Okay, the agenda for today, I will spend the first hour finishing all the topics we're supposed to cover for the exam, and then we'll do something more useful, well, equally useful after that. Okay, we'll get there. So last time we basically tried to do a final case study about asymptotic analysis. We talked about two things. We talked about insertion sort versus selection sort. We already talked about how roughly they should work. Right? If you just refer to the notes last time, I explained to you conceptually how they work. In one case, you keep selecting the minimum. In the other case, you try to keep inserting something into the right place, right? Selection sort versus insertion sort. And our conclusion from last time was both of them are quadratic. You can see for selection sort is n squared, and the other one is also n squared. Asymptotically speaking, selection sort, insertion sort, they are the same. Doesn't matter which one you choose. Okay? But today we're going to see something that's much more efficient. What I'd like to start is, I also make the source code for selection sort, insertion sort available to you. We'll do a little bit more analysis on them just to, for completeness. Okay? What I would like to start today is go over a fragment of code with you just to see how performance will be very bad in terms of array. Okay, what I would like to do now is to go over a little bit slides with you over here quickly. Okay, we'll talk about array. That's the only primitive data structure we talk about in this class. And then we talk about indexing into the array. That's a constant operation. Okay, very easy. Okay, and also we talk about if you want to update a particular slot of the array, that's also constant. Okay. The drawback about using array is when you want to insert something into the middle of the array, or you want to delete something from the middle of the array. That's how things get worse, okay? But we want to see exactly how bad it is. Just give you the answer right away. Every time you want to insert something into some arbitrary middle position of an array, you'll be linear time, which means if you have an array of size 1 million elements, what will be the worst running time? You may have to go for 1 million iteration before you can get to the right spot to insert. But let's see exactly why. I just want to give you a little bit intuition. Because for insertion sort and selection sort, you have to use kind of this kind of loop. So it turns out it will be quadratic. Okay? Let's talk about this example together. Okay? Okay, switch the iPad here. The same fragment here. Let's understand what the method is trying to do over here quickly. Let's say we are trying to implement this particular insert add method. Okay? We simply give one array of strings. And this n over here will just be the size of the array. So it's easier for us to do runtime analysis. And then we want to insert a particular string e. And then we're going to insert into this particular position I. I here we assume to be valid index. Can be from 0 until maybe a.length minus 1. Can be anywhere. Let's talk about the loop over here, the code over here. Rather than going with you one by one, basically eventually you will need two loops over here in parallel, not nested. Okay? Let's see why we need those two loops. Okay, let's see very quickly. Let's say we have a very simple example here. We got insert at. Let's say we talk about an array that's already we got Alan, and we got Mark, and we got Tom. Let's say we got these three names already. The size is simply just 3. So the problem size is 3. We want to insert Jim, a new string, into position 1. You can think about after that, we would like to make position 1 over here to be Jim. So now, what would be the running time of achieving this? Can a constant time algorithm achieve this? That's a question. The answer is, turns out to be not the case. Okay? Conceptually, how do you do it? Okay? I'm going to run the loop together with you. Okay, conceptually. In order for me to really get to this is the input array. To get to the output array over here, there are basically 3 stages I need to do. Stage number 1. Because I'm going to insert into index 1, okay? Eventually, I'm going to put Jim over here. So this is just to assign Jim to the corresponding spot. Okay, just Jim. So this is exactly this line of code over here you will see at position I assigned to Jim, for example, right? So this is constant time operation. That's okay. But what about before that and after that? How do we do it? Basically, you can see Alan, Mark, and Tom. Somehow they have to be copied over into the new array. But how do we copy them over? You have to divide into 2 stages. Okay? Stage number 1 over here. Before this target index over here, we have to copy everything to the left into the corresponding position. For example, Alan should be going to Alan. Okay, so this is basically the stage you see over here. Okay, you can see I'm trying to copy over from index j into index j. J will be starting from 0 until I minus 1. Okay, that's the first stage. And then after that, I'm going to copy over Jim into Jim. Okay, that's what I'm saying over here. What about last stage? The last stage is going to be something very similar, but now we have to be careful with the indices. For example, over here, you can see now I want to move Mark at index 1 into index 2. Right? You can see the index over here is different from 1 to 2. Similarly, from 2 to 3. So now, basically, that's what you will see here. Result at position j is assigned to A at position j minus 1. So that's kind of the index offset you have to take care of. Okay? So now, I'm going to say result, for example, result at position 2 is assigned to A at position 1. In that case, I'm going to copy Mark over here. And after that, result at position 3 is going to be assigned to A at position 2. And then I'm going to copy over Tom. Okay? You can see the 3 stages of effects over here. But now, what would be the running time overall? Would it be constant? Definitely not, because you're trying to copy over everything, right? Intuitively, you can think in this way. We are basically filling in elements into the result array one by one. So there's no way around. You have to copy everything over and fill in the array one by one. What's the size of the array? The size of the array is simply like this. The size of the array is going to be a.length plus 1, because we are inserting one more element into it. Right? So now it's going to be big O of n plus 1, which is just big O of n. So that's a constant time operation. Let's go a little bit deeper. Okay? If you look at the code, specifically if you look at the indices for the j, you can see for the first one is simply of this particular index, and for the second one is over here, and the second one in the middle one is I. Okay? If you think for every iteration over there is simply just constant. You can see for every iteration for the first loop is simply just constant, and every iteration for the second loop is also constant. So now the idea would be how many iterations do we need in total, right? So now think about the bounds for the loop counters. For the first one, it's going to be from 0 until I minus 1. And then we also talk about I over here. And then what about the third loop over here? It's basically from I plus 1 all the way to n minus 1. Okay? So these are the range of indices that we are trying to do. For every one of them, we're going to do a constant time operation for copying over the array contents. So overall, how many do we have? If you think about it, it's simply just going to be n. So there'll be n copying to be done. Okay, so this lesson here is just simply trying to show you if you want to insert something into the middle of the array, you just have to do a linear time operation, because eventually you got to copy all the old contents into the new array. That part is already linear. There's no way around. Okay. Any question about this? Yes. You mean over here? Are you talking about this guy here? Yeah, so yeah, eventually we will see n plus 1 over here. Oh, you mean this guy here? Yes, eventually, right. So here you got from 0 to, let me be more precise over here. So for the first loop, you're going from 0 until I minus 1 inclusive. And over here, so in total, you actually got I. Okay? And then over here, you just got 1. Over here. And then for the final loop, you're going from I plus 1 all the way to n minus 1 inclusive, because n minus 1 is the last index that's valid. Right? So now you get a plus. Well, how many numbers are there from I plus 1 into n minus 1? Okay, you can do, I'll just write it down. You'll be n minus 1 minus I plus 1. Okay, the front minus the end, the n plus 1. You can simplify it. But it turns out, in this case, either you can calculate either n or n minus 1. Asymptotically, it would just be linear. Okay. Yeah. Guys, any questions? So two things you should know. Number one, conceptually you should know that inserting into an array or removing from an array is expensive. It's linear to the size of the array, number one. Number two, if we give you something like the code above, you should know how to derive the asymptotic upper bound. You don't necessarily have to calculate the precise number of primitive operations, but you should know how to define the asymptotic upper bound, the tightest. Okay, big O. I would say, again, so it depends how we ask you, right? If we say you want to calculate the precise number of primitive operations, in that case, yes, you got to be precise. If you simply say, give us the tightest asymptotic upper bound, how I explained it up to now would be acceptable. Okay, yeah, depends. Okay, that's about the inserting into an array, just for completeness. Okay, so now I want to just go over, okay, basically that's, again, an overview for selection sort versus insertion sort. Let me just review the essence for these two very quickly, side by side. When you talk about selection sort, you're basically going to, for each iteration, you're going to select minimum from the unsorted area. In the beginning, it's going to be entire unsorted array. So in order to find out the minimum, it's going to take n time, right? You may have to scan through the entire array. And now, in all the subsequent operations, you're going to reduce the size of the unsorted area. For example, over here, we reduce it from n into n minus 1. So that means now to select the minimum, it will be n minus 1, right? You keep going until the last one is only one particular element in the unsorted area. So there would be just one to select the minimum. So the way you calculate the runtime for that would be big O for selection sort, big O of m plus n minus 1 plus n minus 2 plus all the way to 1. Okay, and we talked about this arithmetic sequence last time, and it would just be big O of n squared. That's selection sort. Okay, I'm going to show you the precise code in Java a little bit, but without tracing it. Okay, that's about selection sort. What about insertion sort? It's very interesting to really look at these two side by side because it turns out asymptotically they will be the same. However, the way you calculate it is in the reverse way. When you talk about insertion sort, okay, that means in the beginning the sorted area is simply just empty conceptually, right? So now whenever you're trying to make a new iteration, you're going to simply select the first one in the unsorted area and then insert that into the sorted area so that it remains to be sorted. Okay, it's similar to what you did in lab number 6 about insert into sorted sequence. So now, in the very first iteration, it takes only one, because if that's already empty, just insert it. Okay? What about the second iteration? If given that you already got something already in the sorted area, how do I insert this guy over here into it? You can either insert into here or insert into here, either less than that or larger than that, either way, right? So that would be 2. And then in all the subsequent iterations, you're going to be increase the size of the sorted sequence that you want to insert into. Okay? So go all the way to, in the very last iteration, this guy here will just be n minus 1, basically, right? There's only one left. How do I insert this guy over here into here, right? It can be in the beginning, it can be somewhere in the middle, or it can be at the end, right? So it turns out it will take about n iterations to find out in the worst case. Okay? So now if you add them up together, okay, you will see a very similar sequence over here. It's going to be big O of 1 plus 2 plus 3 plus all the way to n. Okay, and it's going to be just big O of n squared still. You can see the two algorithms work differently. However, asymptotically, they add up to be the same. So which one should you choose? It doesn't matter. Okay. One more thing to mention so we can make some nice connection later. So what does the running time of big O of n squared really mean? What does that really mean? If you got input size 1,000, for example, let's say you got 1,000 elements in the array that you want to sort into the non-descending order. If input size is simply 1,000, that means you want to have 1,000 squared, which would be 1 million. In the worst case, you need 1 million iterations in order to sort a 1,000 element array. That's selection sort or insertion sort. What we want to see today is another algorithm called merge sort. In which case, if you can have something called end log n. So now, think about how much improvement we can make. Let's say we still talk about 1,000 over here, okay? So that'll be n log 1,000, roughly is 10, roughly, okay? So that'll be 1,000 times 10, which would be 10,000. So we talk about 10,000 iteration versus 1 million. So you can see n log n algorithm is much, much better asymptotically, especially when your n, the input size gets very large. Because log n is a very cheap function to have. But how do you really get to log n? We'll see towards the end. Okay? Okay, final thing about the selection sort and insertion sort. I do have the source code for you. Okay, if you go to the, I'll make the source code available to you. Okay, you can look up in the lectures website. Okay, tracing these two algorithms will not be required. Okay, but if you're interested, go ahead and let me know if you got trouble. Okay, what I would like to do is, let's imagine if I simply give you this source code directly, how do you come up with its tightest asymptotic upper bound? That's the question. Yeah.
Can we reduce that function to just the number of lines that are being run, not the number of primitive operations?
Yeah, so basically in the exam, we will be very explicit to you to say, okay, for this particular question, we want to calculate the precise number of primitive operations. In that case, you got to calculate precisely, right? If you didn't say it, you can assume you just calculate roughly. And then what you're going to do is exactly what I'm going to do right now. Okay? Okay, guys, the question for you, okay, I'll give you maybe about 10 seconds very quickly. Let's say you're given this. What should be the tightest asymptotic upper bound? And then let's say for now, you don't have to calculate the precise number of primitive operations. You don't have to. Just tell me. Okay? Again, we said before, having two nested loop doesn't really mean you got quadratic. Doesn't really mean that. Doesn't have to be. It could be, but doesn't have to be. Stephen? It is quadratic. That's okay, right? But we're going to see exactly why. Okay? Let me tell you what a satisfactory answer would be in the exam. So whenever you're given any code involving loop, especially nested loop, the best way to go for that is to look at the changes pattern for the loop counter. That's the best way to do. Okay, we did example last time already. So this one is no harder than that, no harder. Okay, let me just tell you straightforward, right away. Okay, first of all, you would agree this guy over here is big O of 1, okay, constant. And also this guy over here, we're simply checking some if condition and then doing some assignment. That's also big O of 1, okay? And also this guy over here, we're just doing 3 assignment. It's basically doing a swap of 2 variables, okay? That's also big O of 1. All the bodies of the both loops are simply just constant, meaning that the running time for the overall algorithm depends on how many iterations we have. So let's look at the counter, how the loop counter change over time. Okay, so now I already highlight the part you should really look at. Number 1, you get outer loop, you got I equal to 0 until n minus 2. Okay, I'm going to write it down. I will be starting from 0, 1, 2, all the way to n minus 2. Okay with that? Start with that first. And then, if you look at line number 4, if you look at line number 4 over here, you can see the value of j depends on the I, especially it's initialized to be I. And then every time you try to run the inner loop, you got to increment j. Okay, so it's terminating. It's not running forever. So now, for example, when I is equal to 0, j will be, let me use a different color. When I is equal to 0, j will be from 0, 1, all the way to n minus 1. Agree? Similarly, when I is equal to 1, j will be initialized to be I, which is 1. 1, 2, all the way to, again, the same upper bound, minus 1. Just do one more. When I is equal to 2, j will be from 2, 3, all the way to n minus 1. And the pattern goes on. The last value possible is for I being n minus 2. So j will be n minus 2, all the way to n minus 1. Okay? So far so good? I'm just basically just doing exactly what's specified in the loop headers. Let's now count the number of iterations. Over here, you can see that over here, how many iterations do we have? N minus 1. Agree? Good. Okay, I assume you're okay. From 2 into N minus 1, it will be N minus 2. Agree? Okay, and then over here, it will be N minus 3. Now you see the pattern over here. And then finally, from N minus 2 to N minus 1, you got just 2. All right? So now, what we're going to do is we know that for the body of the loop, every one of them is just constant, so we can already drop them. Okay? All we got to do is N minus 1 plus N minus 2 plus all the way to 2. It's going to be an arithmetic sequence, right? So now it will just be big O of the head plus the tail multiplied by the number of turns. Okay, how many turns do we have? N minus 2 in this case. Remember, we're starting from 2. Okay, you can now check that by yourself. Oh, actually, no. Here, we're starting from 2 over here, right? You can see it's from 2 all the way to N minus 1. Yeah, so you got to look at the series we're talking about over here, right? Of course, if somehow you just got the either of 1, plus 1, or minus 1, in the exam, it's not going to cause you to fail, for sure not.
Yeah, but aren't we looking at, because we're looking at the number of iterations, doesn't that depend on I?
It does.
And I includes, it's from 0 to includes.
Yeah, so you can think about, you go from 0 until N minus 2. So in total, you got N minus 1, right?
Okay.
Yeah. Okay, guys, anyway, so up to now, you don't necessarily have to simplify it if you're confident what the highest power is, right? What's the highest power over here? Well, you can see we got N over here, and also got N over here. The highest power is going to be big O of N squared. You'll be acceptable if you say the highest power is simply N squared, so you don't have to simplify. But be careful. Make sure you choose the highest power correctly. But what we want to see in this kind of question is if you can really derive the patterns of changes of the loop counter. That's the key, okay? Any question about this? And of course, I didn't really trace together with you about this particular selection, so I'll leave that to you. It's not required. But for your curiosity, you may want to do it for your knowledge, okay? But at least, given the code, you know how to derive the bounds. Okay, let's do insertion sort very quickly. It's kind of interesting because asymptotically we know that eventually insertion sort will give us the same running time. Let's do it to make sure. This one is a slightly different pattern that will add up to be the same. Okay, slightly different. Again, we're going to look at all the body of the loop. You can see this guy here, big O of 1, not a problem. How about this guy here? Also big O of 1. Okay, decrement, and also this guy here, also big O of 1. So now we know that all that really matters is about the number of iterations we have for this particular loop. Okay, how do we do that? Again, I highlighted the loop counters for you, just make it easier. Okay, but of course, during the exam, if you're given something similar, you should really highlight the part you really need. Okay, let's say for this guy here, line number 2, I will be starting from 1, 2, all the way to N minus 1. Agree? Okay, that'll be the last value that's available. That's valid for I. And then we say the following: J will be initialized to be I. And then we'll say J minus minus. Rather than saying J is assigned to I and then J plus plus, right? It's different. And notice that in the while condition here, it's saying that we're going to stay in the loop as long as J is larger than 0. So it's basically counting downwards as opposed to upwards. That's insertion sort, okay? Let's see how to patternize this. When I is equal to 1, we know that J is going to be 1. And then, is J going to be 0 when we run this loop? Not really, right? Because we say that J must be larger than 0. So this is the only one. Okay? Let's go one more. If I is equal to 2, J is also going to be assigned to 2 initially. And then, after the first iteration, we're going to decrement J from 2 to 1. So we are still okay because 1 is still larger than 0. Can we decrement further to execute in the loop? Not really, because it will be 0. Okay? Let's do one more. What about when I is equal to 3 over here? when I is equal to 3, so now in this case, j will be initialized to be 3, and then we decrement to 2 and decrement to 1. Okay, let's see the very last iteration for the outer loop. The very last iteration goes like this. I will be n minus 1. In that case, j will be initialized to be I, which will be n minus 1. Decrements n minus 2. Decrement n minus 3. All the way to 1. You can see it's a different pattern of changes. Okay? So now let's count the number of iterations. If you want to count it, it seems to be easier than the selection sort, but turned out to be the same. So what I will do is, it's going to be big O of 1 plus 2 plus 3 plus all the way to from 1 until n minus 1, n minus 1. Agree? So now, how do we add it up? Big O of front plus the end multiplied by, how many turns do we have? N minus 1, right? Okay, divided by 2. Okay, up to now, you're done. You don't have to simplify any further. You don't have to. If you wish, feel free. And then we're going to choose the highest power. You can see we got n here, and also we got n here. So the highest power should be big O of n squared. So it turned out to be the same. I'm going a little bit faster as usual, but I'm just hoping that this is kind of the precision you want to have during the exam, right? Any questions? Okay, so the conclusion is selection sort, insertion sort, they are not too bad as long as n, the size of the array, is not too big. But if you get to be too big, you're going to run into trouble. Your computer is going to slow down. That's why we need something better. We'll get there. Okay, so now I will go ahead and talk about another topic here. Okay, so we are done for this particular lecture here. Okay, so it's done. Everything has been talked about. Okay, let's now switch to your recursion lecture. Okay, there's a certain part we want to finish. Okay, so this is one of the examples that we did previously, just to see, given an array of integer, we want to see if all the numbers there are positive. Okay. And also, you have done lab number 6. Hopefully, this one is quite trivial to you right now. But it's good. We can use that as an example to talk about two things. So 2 more things about recursion. Number 1, we want to calculate the running time, asymptotic upper bound, number 1. Number 2, we want to prove the correctness of your algorithm. Let's do running time first. Okay? Intuitively, we are basically trying to have the 2 indices from and to, and then moving the from incremented by 1 each time until it gets to be exactly equal to 2, right? That's basically what we're doing. It turns out we're just scanning through the entire array as if you're running a loop throughout the array, okay? So that should be just linear. But now, how do we know that it should be linear? That's the question, okay? To really see that, I would like to show you some illustration over here, and then we talk about it. Okay, the same algorithm over here, the same, okay? And we got the 3 cases over here, okay? So we got 2 base cases over here. So you can see over here, when we talk about from is strictly larger than 2, that's the empty array, okay? On the other hand, when from is equal to 2, it's referring to array of size 1. If you think about it, when from is larger than 2, right? So that means nothing to talk about, just empty array. On the other hand, when from and 2 are referring to the index, so that's the array of size 1, right? That's like a subarray. That's something we keep talking about previously. Okay, and then we have another case over here. Let's see how that goes. The other case is the recursive case, which is in the else part over here. Okay, for the else part over here, you can see we simply return a at position from. Okay, from, and then we're making a recursive call. From plus 1 until 2. So from plus 1 is here until the 2. Right? There are 2 parts over here. Okay? So now, the recursive case is when the size is larger than 1. That's not the base case. Okay? So now, how do we talk about the running time for a recursive method like this? Okay? The way you derive the running time is just like the way you think about how things work. You talk about base cases, and also you talk about recursive cases. Let's do this one together. And then we get to binary search. We can also calculate running time in a similar way. The way we're going to formulate the running time is using t. Okay, you can think about t over here is the running time. Okay, and then we're going to give some number over here, so this will be the input size. And you have to state a few, usually a number of relations. It's called a recurrence relation. Okay, recursive functions, basically. Okay, so how do we do that? Okay, let's do one by one. Usually start with the base cases. So now let's say for base case number 1, when from is larger than 2, we simply return true. Return true, constant. So that's why you can see when the input size is simply 0, which means empty array. That should be just 1, constant. Okay, that one's easy. What about the next one? Let's say we talk about when from is equal to 2, and then we're going to return a at position from is larger than 0. In that case, input size 1 also is 1. Okay? Because here, returning this is simply constant time operation. The recursive case is a little bit trickier, but it's not too bad. Okay? You want to think about what's the input size you're trying to call recursively. Okay? Specifically, if you look at that over here, I'll highlight it to you. You can see when we try to make this particular recursive call, so that else part is the recursive case, we are basically saying from plus 1 and 2. So that's the input size. Okay, for the recursive call. What's the input size for this? Think about in this way. If I say over here, I'll make it more explicit for you. If this particular guy here, from to 2, is of size n, what would be the size starting from plus 1 until 2? Would it be n divided by 2, n plus 1, or n minus 1, right? You can see this guy here is simply n minus 1. Let me repeat again, okay? What I'm trying to say is, when you are trying to make this particular recursive call, okay, you started with from and to. So from and to conceptually is this part of the array of this particular size, from and to. When you are trying to make this particular recursive call further, you're saying from plus 1 and 2 remains the same. So that means you're talking about from plus 1 and then for this part here. So you're really talking about this part here, excluding this element here. So the size of the input you're talking about is strictly minus 1. Okay? So now that's why you would say that if I want to calculate the running time for t of n, I should definitely make a recursive call on input size n minus 1 because I say from plus 1, right? And then what would be the plus 1 over here? Plus 1 is basically whatever else you have to do. You can see we have to calculate whether a from is larger than 0 and also do some logical operation. That's constant. Okay? Any question about this? I'm just trying to show you how you can translate your code over here into 3 equations over here. Okay? That's something you'll be expected to do in the exam. Any questions? Okay, that's the first part. The first part is about going from the code into recurrence relation. Okay? Of course, the ones we give to you in the exam will be not too hard, not harder than this, similar. Okay, so now I will show you how you can solve the recurrence relation, easy ones. Okay, so now we'll talk about this guy here, and also this guy here. Okay, like this. All right, we got 3 equations over here. So now basically we talk about base cases over here, input size 0 or 1, or input size n in general. How do we solve it? The principle is you want to unfold the recursive case in such a way that you can see the pattern of getting towards the base cases. Okay, unfold, that's the key word. Okay, I'll show you exactly what I meant. Okay, let's start with the recursive case over here. I would say t of n by definition is going to be t of n minus 1, right? The strictly smaller input size, and then plus 1. Okay, that's what I have. Let's unfold one level. Okay? The way to unfold it, I'll be careful doing the very first step. Think about I'm trying to unfold n minus 1, which means I'm going to substitute n over here by n minus 1, n over here by n minus 1. Okay? So now what I would get is something like this. T of n minus 1, minus 1, n minus 2, and then plus 1. More precisely, you can think about this guy over here is T of n minus 1. Guys, the very first step is really important. Okay? Tell me if you got any trouble with this. We're going to do something very similar for even for more complicated case as well. We're basically going to keep applying this recursive case and see what would be the pattern for me to get eventually to the base cases. Okay? What about we do one more? Okay? So now what I want to do is, let's now unfold this particular guy here, n minus 2. So that means now n over here will be n minus 2. And also the n over here will be n minus 2. Okay? So now what that would be is T of n minus 2 minus 1, n minus 3. Okay? Plus 1 over here. Okay? Parenthesize that. And then plus 1 from before. And also, okay, let me just bracket that correctly. And also plus 1 from before. Okay? Like that. We have already unfolded twice. You have to somehow imagine you're going to keep unfolding this until you get to the base case. Okay? What will be the base case, for example? Let's say T0 or T1, doesn't matter. Okay? Let's say T0. That's a little bit easier to see. So now I'm just going to say I'm going to continue with this particular pattern of unfolding, and then it should be equal to, okay? Eventually what I want to get into is, let's say T1, T0, let's say. T0, eventually. And then T0 plus 1 over here is simply just going to be T1. Agree? Okay? And then you have to somehow imagine that the pattern is actually going to continue, right? Okay, let me just copy over what we got before, and then we got to discuss it to see how to conclude. Okay, so now you got the green plus 1. Also, you got the pink, also plus 1. Okay, let me just make some space for me. Everything is on the slides. I just want to do it in front of you, so it's easier for you to see the pattern. Okay, and also the dark plus 1. Okay, let's not worry about the parentheses. Now, what we can see is this guy over here will be just 1. How many plus 1 do we have over here? That's a question. I heard n, but how do we see it? Right? That's a question. Let's see. The pattern goes like this. You can see over here, that will highlight it to you. You can see when we say minus 1, we actually got plus 1. When we have minus 2, we got plus 1 and plus 1. Right? So now also when we got minus 3, we got plus 1, and plus 1. So now how do we rewrite this guy over here so that we can see the pattern? Right? n minus n, exactly true. Okay? So that will be T of n minus n. So that means when we got n minus n, so that means we got plus 1, plus 1, plus 1, n terms. Okay? So eventually, you will just get big O of n, linear. Okay? I'm just being a little bit informal here, but it's formal enough just to get your intuition. My experience showed me that usually students struggle with the very first step. So make sure you're okay with substituting it. Okay? Any questions? Okay, this one's easy. It's linear. We're going to see something that turns out to be log, which is not too bad. You just got to watch the pattern of changes. Okay, so we'll talk about running time. Okay, and then now we want to talk about how do you prove the correctness of this particular recursive method. I'll talk about one example today. I'll give some practice questions so you can get prepared for the exam. Okay, so also you can ask me during the exam review sessions. Okay, let's talk about this quickly. So now what we have over here is like this. We're given this particular AllPositive method, which will take integer array. And also we got this particular recursive helper method, which take the array from and to. Okay, again, the way for you to think about it is you got base cases over here, when from is larger than 2. Also, you got array of size 1 when from is equal to 2. And also, you got recursive case when just else part. Okay, we got 3 cases. How do you actually present the proof? Okay, I'm going to use a little bit of slideshow to show you. The idea would be you're going to prove by mathematical induction. Okay, I'm sure you have seen this more or less in your previous math courses. I'll just show you the pattern of how to use it. Okay, the idea is simple. You prove for base cases first, empty array, and also array of size 1. Those are easy. And then you assume the recursive call is correct, being the inductive hypothesis. And then later on, I'm going to use that inductive hypothesis to argue the whole thing. That's basically the roadmap. But let's see exactly how you can do it. So by using mathematical induction, we want to prove that the recursive helper method, first of all, line number 2. Okay, we don't talk about the overall method in line number 1 just yet. We will. Okay, for line number 2. So we are going to prove that this particular helper method, which got from and to, it is correct. How do we do that? Again, the picture goes like this. We're going to talk about empty case, and then size 1 case, and then we talk about recursive case. Okay, look at the diagram side by side. We'll do that. Base cases. For empty array, we know that there's no positive number, so the result should be, let me say it again. In the empty array, we know that there's no non-positive number, there's no violation case, so that everything is positive, right, as we said before. So that should be returning true. That's how we expect to see. Is the method returning true in this case? Indeed. How do we know that? You're going to say, look at line number 3, is returning true. You are going to see in the proof, always talk about what you expect to see, number 1, and then compare with what's actually being produced by your program. Yes?
Are we expected to write our own recursion?
Will you be expected to write your own proof for the recursion?
No,
yes.
Like a recursion method itself.
Oh, the recursion method itself, yes, it might be. It might be. Right? Maybe some simple ones. So I would say, talk about the exam a little bit later. Yeah, just make sure you ask me their questions. Okay. All right, and then the second base case is if the array is of size 1. So how do we know if all the numbers are positive? You simply compare the number, right? And in that case, we can look at line number 3 over here. Line number 4. We say A at position from is larger than 0. It depends. So it will be line number 4. So what we have done so far. Okay, let me show you. You can see in the empty array case where from is larger than 2. In that case, we simply say it's returning true. That's correct. You cannot find any violation case. For the case of array size being 1, in that case, we're only talking about this particular elements. How do we know if everything there is positive? Well, you simply calculate it. Right? So that one is also fine. So we proved the base cases already. So now the inductive case is a little bit trickier. It's not too bad. I tell you the overall picture over here. This is what we want to do. Eventually, we want to prove that from until to, this part here is correct. Eventually. How do we know if the blue part is actually correct? We split into 2 parts. Okay? First part is we're simply going to do the following. We're going to say we assume whatever that goes from plus 1 until 2, which is a subarray over here. We assume that this part over here is correct. We assume. Okay? So this is the so-called inductive hypothesis. Okay, this part here is the inductive hypothesis. We assume that this is correct, which means it's going to tell us for this particular part of the array, excluding this particular element over here, excluding that. Either everything is positive or not. And then we're going to combine this particular result together with whether or not this element over here is positive or not, right? That's basically what we're doing. So what do you have to write in the proof? Okay, let's look at that. Again, you're going to split into this part here, which you assume to be correct, and also combine with this part, which you have to compute. Okay, 2 parts. Let's go back there. So inductive cases, number 1, you make an inductive hypothesis. You simply say all positive helper from plus 1 until 2, right? Exactly the subarray I just talked about. Assume that it is correct, which means it returns true when every element in there is positive and false otherwise. Okay? Assume that. And then we have to somehow argue informally or write it down. to tell the reader what does it really mean for the blue part over here to be all positive. It simply means everything here is positive, right, in the subarray, and also this single element here is also positive. That's how we combine the two facts. And that's exactly what I'm writing here. And then finally, you have to say this one can be done faithfully by my program, because if you look at line number 5 here, I'll highlight it. If you look at line number 5 here, okay, if you look at that, that's what we're calculating. And now let me annotate that a little bit. You can see this part over here is the recursive call. So this is something we assume to be correct, which is the inductive hypothesis. That's what we assume. And then we're also trying to calculate A at position from, which is this guy over here, right? And that's larger than 0. And then we combine these two things together using conjunction. Okay, that's how we calculate. All right. Okay, let's go back here. And then what we have done so far, we are only trying to prove that this particular recursive helper method is correct. That's all we have done. One more step. The original method, which is all positive, that takes a single array without the from and to. How do we prove that it is correct? Basically, what we're going to say is, given that from and to being arbitrary for this particular recursive helper method would just be correct. So now, if you go back there, the original method we just call from 0 until a.length minus 1, which will scan the entire array. So that means it must be correct as well. Okay? So now, if you go back there, let me just show you this part here. Okay, I'm just duplicating this. So the last part you want to be careful about is, you can say, since we want to prove this, okay, now we want to say, given 0 and a.length minus 1, so these will give us the entire range of the entire array, the entire range. Okay, which is exactly what we're doing here, right? Line number 1. You can see you also got to mention the line number. Okay, all positive, and then 0 until a.length minus 1. Okay. It might take some time for you to absorb the details. I'll also give you a little bit more example to practice. But what about the overall picture, the steps? Base cases are not difficult to prove. Okay? It's mainly how do you make the inductive hypothesis, right? I would say in the case of the array, you have to basically make the hypothesis on the recursive call. Okay? Because recursive call is guaranteed to be done on a strictly smaller input. Okay? Okay, any questions? We okay? Any immediate questions for me? You okay? All right. Okay, so now I would like to do 2 more things, if possible. Okay, number 1, we want to talk about something called binary search. Okay, what's a binary search? We talk about how you can search through an array over here. Let's say the array is of size n. I want to say I want to search for a particular key value k. Okay, what's going to be the worst running time for this? Well, it's going to be linear, right? Because I might just be unlucky. The I element might just be here. In that case, it would be big of n. Okay, that's a linear search. Okay, now let's make a small assumption on the array. Okay, let's say the input array is sorted in non-descending order. For example, it might be sorted in 1, 2, 4, 6, 7, 8, etc. It's sorted. But now we want to know, is it possible to search through this array not from left to the right? Is it possible, right? Let's say this. In general, I'm going to show you the code in just a moment. Let's say this is the array from 0 until a.length minus 1. Okay, you can think about its n as well. Okay, that's the size of the array. Okay, let's say this. Somehow I calculate what's in the middle. Okay, the middle is simply a.length minus 1 over here. Okay, a.length minus 1 plus 0 divided by 2. For example, let's say this. If I have an array that goes like this, if it's from 0 to 9, in that case, the middle part, it was just with index 9 plus 0 divided by 2, which will be 4, roughly in the middle. Okay? let's say I calculate the index of the middle, and then let's say I want to compute whether a key k exists in the array. Okay? Let's say hypothetically, if I know A at position, A dot length, if you allow me to make a variable here, can I just say this is called the middle? Okay, it's a middle index. If I say A middle is larger than, I'll make it easier for you. If k is strictly larger than A at position middle, let's say, can you actually tell me whether should I go to the left or should I go to the right or should I go to both?
To right.
Why is that? How do you guarantee I wouldn't miss anything?
Because it's already sorted in non-descending order, so there's going to be no elements to the left.
Mm-hmm.
Left.
Okay, so basically here's the insight into binary search. Okay, given that the entire array is sorted. Okay, entire array. So now we are saying that A at position middle is actually smaller than k. Would this element be smaller than k as well? For sure, because everything to the left of the middle part is all smaller. Okay, if you think about it, you can think about every element here is smaller than 8 at position middle. On the other hand, every element over here is strictly larger than 8 at position middle. So now, our initial assumption that the array is actually sorted is a very powerful assumption. Because if we can assume that, so that means you can always just go to the middle part and then decide whether you should go to the left or go to the right. That's basically what we are doing here. Okay? That's binary search. But why would that be more efficient than linear search? Intuitively, you can think in this way. Intuitively, if I know that k is already larger than A at position middle, so that means my search space, rather than the entire array, rather than that, is only going to be just this part over here. And what's the size of that part? It's about half of the array. So now, if I continue with the same logic, I can keep halving the array size that I'm searching for. So now, if you go for that, eventually you're hoping that you will get to an array of base case, like either empty size or 1. How do we get there? They will involve something about log, but we'll see. Okay. Okay, I do have the code for you over there. I'll trace one of them together with you just to get some idea. Okay, and then we'll talk about the running time. Okay. So now let's see here. Okay. So we got binary search over here. We simply got some input array which is sorted, and also we got integer key. Okay. And then we got some binary search helper. Okay, from 0 until from and to. Okay, from 0 until sorted out length minus swipe. Okay, just the entire array. And now let's focus on this particular method over here. Okay, so this is the base case, meaning that if it is an empty array, there's no way key exists. So that means false. Okay, you can see this one is constant time. Okay, or more precisely, t of 1 is simply equal to 1. Oh, sorry, 0. Empty array. Okay? And then if from is equal to 2, that means we're talking about a single element array, right? Subarray. In that case, you just want to know whether that particular element is equal to key. Okay? In that case, we are basically saying t of size 1 should be 1 as well. So these two are just constant. So these are the base cases. Okay? I'm trying to state the running time at the same time so we can solve it together later. And then over here, I'm simply calculating the middle index, which will be from plus 2 divided by 2. You can think about the middle is exactly over here. Okay? And then we are trying to see the middle value. The middle value is simply sorted at position middle. You can think about this is the middle value, MV. Okay? And now we are trying to search for key. And now we have to make a decision. Should we go to the left or should we go to the right? It depends. So now in the case where key is strictly smaller than middle value, should we go to the left or the right? Well, if the key is strictly smaller than the middle value, so that means it cannot be here, right? Cannot be, because everything on the right is strictly larger than the middle, given that it's sorted. So it's not possible. So now the only place we can go is over here. So let me just write down the case for you. Okay? So now you can think about over here. For this particular case, key less than middle value, what we will do is we're going to search for this particular part. Okay? But how do we express that part? The way to do it is, what's going to be the index range for that? It's going to be middle minus 1, right? Starting from here. Middle minus 1 and from. So that's why you see from until middle minus 1. Okay? We're making a recursive call. And then what about the other case? Okay? You go either one, but not both. The other case would be when key is strictly larger than the middle value. In that case, you're basically saying this over here. You're saying key, sorry. You're basically saying over here the key is strictly larger than middle. So that means only this part is possible, only this part. And how do we do that? In that case, you're just going to say, I'm going to go for this part here instead. But how do we express that range? In that case, you can see this particular index over here is middle plus 1. So that's why you see middle plus 1 and then 2, 2. You got two cases, basically. Either key is strictly less than or key is strictly larger than. But what if key is equal to it? That means you have found it. Okay, return true. Okay, that's a binary search. But now, how do we know the running time for this? That's a question, right? Let's look at the running time very quickly. Okay? Before we do the running time, let me just trace one example for you, together with you, just one example. I'll leave the other one as exercise for you. Let's trace one of them. Okay? Let's see the following example. Let's say array A, okay, we got from index 0 until index 8. Okay, we got 9 elements inside, 9. So what we'll do is we want to search into the array for 18. Eventually, we'll see 18 does exist, eventually. Okay, let's see how exactly it's going to work. So what that will do is, let me just see this. So we're going to search between 0 and 8. Okay, this is a from, and this is a to. You can think about this is the initial range of array we are searching for. Okay, and then we're going to calculate the middle. The middle is simply going to be the from plus 2 divided by 2, which will give you 4. So that means we should really compare this index over here, the elements, against 18. Where should we go? Should we go to the right or go to the left? Go to the right, right? Because you can see 18 is strictly larger than A at position 4. So that means we should go there. So now in order to go there, how do we update the index? Conceptually, we are actually going for this particular subarray. Agree? Conceptually. But now, that one there should start with, over here, this is the middle currently, so middle plus 1. So that should be 5 and then 8. Right? If you remember from the previous code, it's going to be middle plus 1 and then 2. Okay, that's that particular case. In that case, you're going to get between 5 and 8. So between 5 and 8. Okay? So now, between 5 and 8, what we'll do is calculate the middle part again. So now the middle will just be 5 plus 8 divided by 2. So that will give you 13 divided by 2. Get a quotient, you get 6. Okay? So now let's find out 6. 6 is over here. Okay, so now according to the middle value, okay, so we got 8 at position 6. Is the key we're looking for larger than it or smaller than it? Smaller, right? Because it's 21. So the K, 18, is strictly smaller than that, so we should go to its left. Agree? So now, how do we calculate index? Over here, if that's smaller, so we should go for middle minus 1 and then from. Okay, if you look at the code. So middle minus 1, middle is over here, 6, 6 minus 1, you got 5. So 5 and 5. Okay? It's a little bit low-level tracing, but eventually you will get to this particular array, 5 and 5. So now, 5 and 5, you got it. Okay, check, you find it. Okay, another exercise for you is on the right-hand side to see how you can trace this particular one. Okay, I'll leave that empty for you. Okay. Binary search is not too bad. I think conceptually it's really easy. Just go to either half. depending on how large the key is, compared with the middle value. Okay? Okay. Let me just go for another one here. How do we calculate the running time? Let's do this one here. Okay, running time over here, we already talked about when the size is equal to 0, it's going to be 1. When the size is equal to 1, it's going to be 1 as well. Okay, sorry, that's not very readable. Okay. Okay, 0, 1, and 1, 1. Okay, so now what about the recursive case? You can think about for the recursive case, we either go for this branch or we go for this branch, and we'll go for this branch, right? Either way. But now for these two, these simply mean we haven't reached the base case just yet, so we're going to go further. Okay, and if you think about it, the size of the array to look at will just be half of the size, right? So now this is why this turns out to be the running time for the binary search. Okay, let me go over there with you, and then we'll do a little calculation together. So now empty array, just 1. Empty array, just 1, return. Size 1 array, it will just be also return something simple, also 1. So now for the recursive case, either go for this way or this way. For either way, the size of the array to look at is n divided by 2. And then, of course, you got to do a little bit like a arithmetic over here. So that's why it's plus 1. So now the question is, how do you solve this recurrence relation? I'll do it together with you, don't worry. Okay. The principle will be you still have to unfold the function to see the pattern. Okay, let's see it. Okay, so I will start with this guy over here, t of size n. Okay, so now by definition, it's going to be t of n divided by 2, and then plus 1. Okay, let's be careful with the first few for us to see the pattern. How do I, by definition, how do I see this guy here? So n is now going to be n divided by 2, okay? N is going to be n divided by 2, and then divided by 2, which would be n over 4. Agree? Okay? So that means it's going to be t of n divided by 4, and then plus 1. And then don't forget a plus 1 over here. Are you okay with the first step? Okay, again, we are substituting n by n over 2. That's what we're doing. Let's do one more, and then we can see the pattern. Let's say, how do we do this guy here? Right? So now n is going to be n divided by 4. So now n over here is n divided by 4 divided by 2, n divided by 8. Right? So it's going to be t of n divided by 8 plus 1. Okay? And then we're going to get, okay, don't forget a plus 1 from the previous one, and also don't forget a plus 1 from the initial one. Okay? I wonder if you have seen any pattern. Let's just talk about it quickly. First of all, you can see this guy here is 2 to the 1. Agree? This guy here is 2 to the 2. This guy here is 2 to the 3. When the power is 1, you got just 1 plus 1, just a single plus 1 term. When it is 2, you got plus 1 and plus 1, 2 terms. When it is 3, you got plus 1, and plus 1. You got 3 terms. It seems like the exponent over here corresponds to how many plus 1 you have. So now all we're going to see is when we reach the base case, how can we rewrite it? Okay. So now we're going to say all the way to. So now let's talk about the base case. Let's choose T1. Let's say we do that. What I want to achieve is T. Let me use a different color here. T of 1. And then that one there, which for sure would be plus 1, plus all the way to, okay? Don't forget, you got plus 1 pink, also plus 1, and also plus 1. I'm ignoring the parentheses, just to make it simpler. So now, how many plus 1 do we have? Over here, T1 is just 1. That's not a problem. Okay? How many such plus 1 turns do we have? Okay. N? Log n? But you don't just guess, right? How do you know that's log n? The trick would be, previously we agreed that if you can somehow rewrite the term over here, n divided by 2 to the power of something, whatever exponent it is tells you how many plus 1 terms you have. Can we rewrite 1 over here in terms of that? 1 would be equal to n divided by 2 to the power of, don't tell me it's n. It's not, right? Log n? Agree? Log n. If you have question about it, talk to me after class. Okay? So now it tells me that I can rewrite this into n divided by 2 to the power of log n. Okay? And then, so that tells me how many terms do I have? Log n terms. Okay? Log n times 1, log n. So eventually I got big O of log n. That's a binary search. Okay? You can see it's very similar to what we did before for the linear array algorithm, but just got to be play a little bit more with the pattern. Okay? Any questions? Okay. So now I would suggest the following. I was hoping to actually get to the merge sort today, but I think we're running out of time. So what I would do is as follows. Okay? So there are 2 more examples in your recursion example here. Okay? There are 2 more examples in the recursion lecture. Okay? So binary search, we just covered that in depth. So for your exam, make sure you study up to here. Okay? The next 2 topics will be optional. Okay? The first one is called Tower of Hanoi. That one is quite a challenging example, but it's optional. I would suggest go over the slides. If you got any curiosity about how it works, speak to me. Okay? That's optional. Okay? Although there's another one over here called merge sort. Okay. Another one here is merge sort. I'm sorry that I couldn't really get to it before the end of the course. This I'll mention to the other 2 instructors. We couldn't really cover that in the class. However, I do encourage you to look at that. I will make sure I also cover that in the review session, but it may not be covered in the exam. Okay, I want to make sure at least you can learn about it, the merge sort. Okay, that one there is quite a useful sorting algorithm. I'll make sure I cover that in one of the review sessions, but it's not covered in the exam. Okay, but anything that's similar to linear algorithm on the array, or anything that's similar to the binary search, they are covered. Okay, okay, let me wrap up, and then we'll do something else, okay, for this course. Okay, let me just take a few more minutes. Okay, for this course, we have learned about many things. Procedural programming, so especially exceptions and recursion. You'll definitely learn much more about recursion in 2011 and 3101. Hopefully, whatever you learn here, give you a little basics. Okay, running time correctness, okay? And by the way, correctness is covered, okay? Make sure you study that. We can answer your question in the review session. I'll announce the dates in a bit later. Okay, well, we got data structures, we got arrays, and also hash tables, and also maps. So these are what we covered. Okay, we covered quite a bit about OOP for sure, throughout the course, right? So these are just like a checklist for you to see what you have learned, okay? Specifically, inheritance. We definitely spent a lot of time on inheritance. I thought that's an important topic for you to grasp. Okay, I'll just mention also we talk about debugger. If you haven't picked up the debugger, even though we cannot assess you on the exam, but I'll suggest pick it up. Okay, it's good for you. Okay, the debugger. Also unit testing in JUnits. So now, students usually ask me, what should I do beyond this course? I have 2 suggestions for you. Basically, I would suggest 2 possible books for you. It's not just like a 2-month project, right? You may want to plan this for the rest of your degree. Okay, that's what I would suggest. These are the 2 books. One is about algorithm. The other one is about design pattern. Get the books. They might be used in one of your future courses anyway. So purchase them earlier. Okay, or get access to them. What I would suggest you do is study, for example, for the algorithm book, data structure by data structure, algorithm by algorithm, and somehow try to see if you can translate the algorithm, which is pseudocode in their book, into Java. And then to write some JUnit tests to test your code. I think that'll be a very valuable exercise for you. Maybe even prepare for an interview later, okay? And then also for the other book, it's about design patterns. This one will be used in 3311 later, but if you want to just check it out from the library, they also talk about different object-oriented patterns, which we also talk about in this course, but it's more advanced. You can also do some investment on this. It's up to you. Okay, so that would be my suggestions. Okay, so now whatever you learn in this course, they will be assumed in 2011. Okay, so try to review a little bit 1019 and 1090 during the break. That could be useful for you. Okay, and then do not abandon Java, and then let me know if you got any questions. Okay, and for your exam review, just based on your responses. So that's at the time. Okay, I'll announce that tonight as well. Okay, any question for me? All right, thank you.